Welcome to the Living in the Future podcast, where we bring to light specialized topics from life in the modern age. This episode, I have an interview with Charles Forsyth about the Plan 9 and Inferno operating systems from Bell Labs. Projects worked on after the Unix operating system that is the foundation of every mobile phone as well as the Macintosh computer. For my non-technical audience, the conversation can get a bit technical, but I'd like to frame it as an investigation into a future of computing that never came to be, and yet at the same time is still with us. To the technical audience, please enjoy. Charles Forsyth is a consultant and systems programmer at Terza Rima Systems. He earned his bachelor's and master's in mathematics from the University of Waterloo and a doctorate in philosophy from the University of York. His interests include compilers, operating systems, distributed systems, and embedded systems, networks, and multimedia, all with a focus on minimalism. He has been responsible for the Inferno operating system under the company name Vita Nuova and is an enthusiastic Plan 9 user. Thank you for joining me. Let's start with Plan 9. So, after Bell Labs creates Unix in the 60s and 70s, Plan 9 is the next thing. Is that fair to say?
It was the next thing that became visible externally. I don't know in detail what they were doing internally up to then. I remember attending a talk by Rob Pike quite some years ago now, obviously, where he talked about why they did Plan 9. Well, one of them was that they wanted to be able to experiment. It wasn't so much having operating systems as such, but they wanted to be able to experiment with certain things like devices and CPU architectures and a host of other things that they previously might have used Unix for. But they ran into the problem that even they had, Unix had become incredibly big by then, the System 5 stuff. And it just wasn't a convenient base for research and experiment. And so Plan 9 was one reason. There's a more philosophical reason for, not part of that talk, but a more philosophical reason behind it, which is that Ken Thompson once observed in a talk about Plan 9 that the problem with Unix is that it was done at a time when the operating system Unix was in control of the whole machine, and it thought that was the universe. When networking was added to the system, it was bolted on the side, but at quite a deep level, Unix is an operating system for a single machine, and the network part is used to make TCP/IP calls or UDP calls to various services, but it isn't a fundamental part of the operating system architecture, compared, say, to the central part that Unix's file system originally played. In fact, originally Unix was done to experiment with some ideas about doing a file server, a file store, data structures for that, when networking was added, it was done several ways. The Berkeley people added the sockets, and much later, in what became known as 8th edition, Ritchie added a stream IO subsystem that rebuilt the internal structure of handling of certain classes of devices, including network devices, in Unix itself. Some of that got carried over as an implementation technique into Plan 9. But still, the system is all self-contained, really. It doesn't really regard itself as being part of a networked group of related and cooperating systems. So Plan 9 set out to rebuild to build an environment that they could use for the research, and also to address networking and distribution as a fundamental part of the system structure. Again, somewhere it says that one of the inspirations for it was a system known as the Cambridge Distributed System, in which there were Again, another variant was being developed in Amsterdam, at a university in Amsterdam, in which you had specialized services on the network. In Plan 9, this became the file server, the permanent storage file server, and CPU servers and what they call terminals. And the idea was that you would connect your terminal, log into your terminal, and that would give you access to these shared CPU servers and a shared file server. So there's that level of structure, and the systems were specialized, so the CPU server didn't implement file storage. The file server didn't run user processes, and in fact, the original file server ran entirely in kernel mode, and the terminal was there to provide the graphics user interface. Some of that was modeled and loosely inspired and modeled on an earlier structure for the BLIT terminal, intelligent terminal, that eventually became the teletype 5620, I think, or something like that, DMD display, intelligent display. And the idea was that you would run programs in the terminal that would connect to services on the network, both import the file service and also connect to the CPU service to get the access to bigger multiprocessors. To do that, they devised an architecture that involved these things called namespaces, where you have a small, often quite a small hierarchy of names arranged like a file tree, where the things in it are not files stored on a permanent storage device somewhere. They're if you like, they're just virtual files, they're a data structure somewhere. But you can open the file-like things. You can traverse the namespace, walk down the namespace just as you do with the path name, and you can open the internal nodes of that tree, which are the directories, and get a list of names beneath it. And you can open the leaf nodes, which are you open and then read and write those as you would read or write a file in Unix. And in fact, the whole of the system ends up being structured as a collection of these file trees of one sort or another. So device drivers provide a tree of names that represent the control and the data functionality of a given device. The network interfaces with TCP/IP and UDP and other protocols, again, all are represented as these little file trees. The simplest ones have a control file and a data file. More complex ones have a collection of numbered directories that correspond to individual connections or conversations within that structure, and you can get there's a special convention. There's a convention for getting a new one of those allocated to you to a process to open that and then begin to configure and then make use of the network device. So, but you've got a collection of these little namespaces. So the next step is to provide a few primitives, just a handful of primitives that allow you to compose or compute a namespace for a given application, and rearrange it once you rearrange things inside that namespace once you built it. And that's done using the notion of mounting these little trees, a bit like the Unix mount, but these aren't physical files or files on physical storage. They're, again, these virtual things. Mounting, it's replacing an interior node of a current file tree by the contents of some other service or device that's represented as a small file tree, and doing that consistently throughout the system. So you import a connection service, a DNS service, and you put them in, and you bind in to the namespace devices such as IP multiplexers and a variety of other things. And of course, one of the things you can import and bind into a namespace is indeed one of the, there are several physical file storage services that you can use, including the main file server. So the usual approach is that you start by binding in the main file server, and then you put various devices on top of that, on top of the skeleton for the root namespace of a particular application.
So I actually have a question about that. I have two questions. First off, so the 9P protocol, which is part of Plan 9 that has sort of migrated to other places.
Yes, that's the third thing I was going to mention after the
Oh,
computable namespace. That was that if you represent all your system resources, your major system resources, including DNS SACs, lookup services, making connections to other systems, the network protocols themselves. If you represent all those as little namespace trees, and you have a protocol that converts open, read, write, and close, and a few other system calls like make it create a node, converts those into messages on a protocol. Yeah, superficially, it's a bit like NFS, but the differences are that it's intended not to access remote file storage. It's intended to access, sorry, it's intended to implement, first of all, even locally, the resources that go in the namespace, so that the domain name server on Plan 9 is indeed a 9P server. It's a file server. It serves this protocol to build its view of a particular namespace that it wants to provide for DNS services. So, but once you've got that protocol used to implement services inside the system, all you have to do is put that on a network connection, and you can access the same services from a remote node that mounts that network connection or the file tree that's served by it into its own namespace. The thing I want to mention is that namespaces have a per process granularity in Plan 9. They can be shared, but they can be different at the granularity of a single process. And that also makes a difference. I mean, if you think about the ideal is that you have a namespace. If you have some application running on Plan 9, then you make a namespace that is just what it needs to get its work done. In practice, if you look at the Windows and my Plan 9 machine and as I make a new one, they're all very similar. But you have the ability to build a namespace per process, and that provides having access to a name acts as a kind of capability for access to the service. If you can't import the name or you can't put it in the namespace, then you have no way of accessing it. So you don't need to have all sorts of specially protected system calls and capability, special capabilities to control system calls. You can do it by simply building the namespace that you want to have to restrict it. There's some details that you have to address in terms of the way some resources are accessed, but that's broadly speaking the principle behind it.
So with the 9P protocol, which is migrated from Plan 9 to sort of virtual machine hosts and stuff like that,
Yes,
do
it
you
has.
have the ability to map any of these other more exotic services like CPU or network, or is it mostly just used as file storage at this point? That's
No,
my
well,
first question. And I do have a follow up for the second question, which is I find it very interesting that we talk about how the network is bolted on. I mean, BSD sockets are bolted on to Unix, and yet that's what runs everything from top to bottom. And I
yeah, there's no structural support for that in the sense that it hasn't. It's just a new set of system calls that you can use. So much so that in fact the addressing that if you come to do a completely new type of network, a new protocol, as we did running on BlueGene, where there was a tree network a collector network, and a torus network, and they have very different properties, and they were very different themselves from anything else that existed on in terms of TCP/IP and UDP/IP and the like. Or if you want to do something like, I suppose, InfiniBand, one of the things you come across almost immediately is that the by its is that the socket subsystem makes it quite hard. Oh, you can add extra things, but there's some peculiar implementation restrictions that make it quite difficult to add new types of addressing structure to it.
Other than an IP address space, even
Well,
IPv6
I'm thinking of the sock addr structure,
okay,
which has a see if a big that has a size. It's a data structure and it has a size,
right.
and that's what you have to use to make a connection, and you have a sock underscore dgram sock selection of possible types classes of protocol. It's a
Right.
datagram or a stream. But you start to get an address into it, and it has caused problems in the past when people wanted to add new network types, because you have a compiled binary that has a particular sock addr structure in it, and that can't be bigger. I mean, you can put smaller things in it, obviously, but it can't be bigger. Be made bigger at runtime, sensibly, and so you do get this very early binding of conventions in the socket stuff, which creates problems if you're trying to experiment with new things. But even more than that is this notion that there's nothing. The sockets don't by themselves do anything to help you structure your application or divide things up. It really is just the socket that's described in the TCP/IP and UDP and so on RFCs, that you have a bidirectional stream, and or two unidirectional ones paired, and that's it. I mean, recently I use to refer to those as sort of making TCP/IP telephone calls to remote systems.
Yeah,
There's no, it's a network connection, which is fine. I mean,
yeah,
you need something, even with 9P between systems, you need something to carry that thing. But once you do carry 9P, you have a structure inside that applications can use. They can inspect it. Unlike HTTP, for example, they can inspect that namespace because they're primitives provided by the system to allow you to do that. You can open a directory and read its contents and see what's there. And then there's a rule for making like any directory name path in Unix, you can add a new component following a slash and then move on to the next thing and traverse the structure. And the services are designed to provide the service through some sort of namespace, which conventionally the namespaces are similar for similar types of things. There's also a sort of a composition of namespaces, and almost not, it isn't properly recursive, but a sort of as an example of how the structural thing works, is that there's a service netDNS that provides some names that you can use to look up IP addresses. There's a higher level service called the connection service, CS, and it works which is a separate program. So there's a DNS server and then there's the connection service. And the connection service works by applying. Its idea is that you write a higher level description of the thing you're trying to get to, a network, some name or address of the thing on the network, and a particular protocol or other attributes that are important for making the connection you want to make. And in response, it gives you back a set of recipes. And the way the recipes work is that each line of the recipe is a description of open this thing and write the following thing into this, and that will give you a connection. if it works. If the remote thing is there and doesn't time out and so on. And you can work down a list of alternative paths to get to the same higher level network thing. In the case of domain service names, though, if the network is TCP or UDP and you give it a host name, then the connection server itself turns around and uses the DNS service names file tree that's provided by the DNS service, which has a very similar structure, that you open that, you write the domain name into it that you want to get to, or the IP address that you want to do a reverse lookup, and it sends back. That's done by opening, writing, and then reading. And each time you read, you get a new recipe or new of say an IP address translation in the case of DNS. In the case of CS, you get a new. It takes the results of that and puts it together to form a recipe to say, if I want to get to, I don't know, my file server or my CPU server Lavora, then here's a list of the ways you can do that. And as I said, the list is provided as a set of recipes for the application to follow to get itself a connection. So the connection service doesn't make the connection, but it tells you how to do it. That way, the correct namespace is affected. But that use of one service by another, with the services having the same fundamental structure, that they provide a file tree, is quite important for the overall simplicity and of the system. And it's an example of how the structure of the system is affected by this use of building it up as a collection of namespaces, compared to just having the traditional Unix file store, the special devices, networks as another scheme that you can make network connections, but there's nothing that brings any of that stuff together in Unix. The network is pretty much off on the side. And one of the things about structuring services as these internal 9P services, so the 9P file service, is, as I said, now once you've done that, you can then make a network connection from a client to a service on a machine and read and write the 9P requests on it to give you, in your local namespace, the remote service looking as though it's a local service. But it's actually being done by this remote system, and that's used a lot. And there are a few papers one can look at to see plenty of examples of how the various different types of services are provided using namespaces, and then you can do this distribution and remote access just by serving 9P on a different. When the services are done inside the system, they're typically using, say, a pipe, an internal pipe, and it's just as easy to substitute for the server. It sees a pipe as a file descriptor. If it's a network connection, then it sees that as a file descriptor and simply reads and writes 9P messages, 9P responses to 9P requests coming in on that, and it doesn't know that it's got any distribution scheme going. Put another way, in Plan 9 to do network order, you import, loosely speaking, you import dev audio. If you want to import, if you want to do network graphics, you import dev draw. If you want to import network connections, you import different. If you want to import a DNS service, which I've done on quite small machines, which are too small to embedded machines, too small to run a full DNS service, they simply import it from a bigger machine. And authentication services and other services are done in much the same way. But that's sort of what I meant by the structural support for it, by the use of namespaces and by the use of 9P to implement services within the local machine. And the distribution sort of falls out from that. Also, the error handling as well, because with read and write system calls as the primitive, you're expected to handle errors in those. And so if you have a remote service and it fails, or your connection to the remote service fails, then you get an explicit diagnostic from that, compared, say, to I don't know, having a special system call to get the time. You wouldn't
Right.
normally expect that one to fail in a Unix system. But in Plan 9, those things are accessed using Open Read Write and so on. So the failure is handed back to is made visible, which could then be propagated, in whatever language you're using as error returns or exceptions or something. But at least you know about it. And conventionally, you explicitly check for all those things.
So just to be clear, the 9p that's implemented on virtual machines and in Linux and stuff like that, can that follow these recipes to do DNS access as well? Do they map it for
Yeah,
anything else? Or
I
I
think
think,
I think they can. Well, the slight difference there is that, and it's fairly old now, is that there
yeah,
was a variant I think called 9p2000L, L for Linux, I suppose. That so the original Plan 9p protocol, and the one that's used inside Plan 9 for the most part, does not have, because Plan 9 doesn't have, it has not got symbolic links, for example. One reason is if you want to do certain kinds of namespace remapping, you do that by using primitives that the two or three primitives that manipulate namespaces. You don't do it by putting symbolic links to point somewhere else. So it's explicit. But there are many applications on Linux that, even if you're running in an emulator, that need that expect to have symbolic links, and so 9p 2000 was extended for those purposes to 9p 2000L to provide symbolic links and some other stuff that I don't even know offhand. So 9p 2000 would be a subset of 9p 2000L. So I would expect that the systems that support, well, on Linux or Windows subsystem for Linux, I think at least for a time, the QEMU and some of the other emulators provided did access some things using 9p, or some variant of 9p. And those that should be able to access the Plan 9 services directly, because Plan 9 is 9p 2000 is sort of a subset of that more elaborate one to cater to Linux. The only exception there that I can think of is that, for reasons of efficiency, I suppose, or just being able to implement it at all, I think there are some restrictions on accessing certain kinds of services through the 9p interface from Linux, say, just because something at the kernel level doesn't implement the right state that you would want to get the right effect. One of the things about 9p in any of its forms compared to, say, NFS is that there's state associated with a connection with a 9p channel, a 9p conversation. It's not a stateless protocol, and that has the advantage that the server sees, if you like, the server sees each open, and it has an identifier for each open request. Sorry, each thing that is opened, and it also sees close requests. And they're called clunk in the protocol. And so the server does have a notion of a session. It has for each connection. It can multiplex that connection so that several processes on the remote side can be accessing the same service through the same connection, and it can keep track of which ones are which you can't do with NFS as such, for example, because because of its stateless nature, and closes are sort of advisory if they exist at all. And it isn't possible for a CS or a DNS type service to provide the same functionality as in Plan 9 because it doesn't reliably know who the consumers are, um, who the client processes are,
Yeah.
um, or client connections. Uh,
So that's the operation on the file system of Plan 9 for the most part. The file system, the network, it all appears as though it's files.
yeah,
What
little namespaces.
namespaces as well? What did they do with the GUI as well with the Rio or Rio windowing system?
Well, the same. Yeah, well, both. Well, there's the original Windows system was 8.5. The later one
Oh
was
yeah,
Rio.
yeah.
The later one was Rio that added some other functionality, and it takes the same approach. There's also a text, sorry, what I call an integrating development environment, which is, but it starts off as being it's also one of the text editors called Acme, and all three of those programs make use of the namespace in various ways to structure the thing that they're handling, graphic, keyboard and mouse input, for example, other kinds of input as well.
So
If you
that would actually follow you if you went to
well,
another
well,
machine.
so I mean, broadly speaking, it's easier to do it a slightly more abstract thing than picking up particular details of those things. But broadly speaking, the idea is that if you're multiplexing, you give each window its own. Um, uh, yeah, suppose your input is a dev keyboard, dev mouse at the outermost system level, that the corresponding to, if you like, the keyboard that's plugged into your machine or connected through Bluetooth, or the mouse that's plugged in or connected through Bluetooth. And those devices have got names, dev mouse and dev keyboard. What the what the Windows systems do is they give each window, the Windows system serves, for each window, it serves a little hierarchy that has the names dev mouse and dev keyboard in them. A process that you could run at the outermost level without a Windows system that would open dev mouse and dev keyboard to get mouse and keyboard input um, will will run. But you can then take that same program and run it inside a window. It opens dev mouse and dev keyboard um, as conventional names and reads from them to get mouse movement and positioning, and reads from the keyboard to get the characters being typed. And it's unaware that it's running in a window. Instead, the window system multiplexes, has a collection of namespaces, if you like, one per window, and it multiplexes the real thing. It multiplexes the dev mouse and dev keyboard that it opens across those virtual little device trees for each window. But that also means you can take the Windows system itself and put it inside one of the windows, and it opens dev mouse and dev keyboard, and then it ends up multiplexing those across the windows inside that space. And a similar sort of multiplexing. It's a little different in detail between 8.5, say, and Rio, but there's a similar kind of multiplexing to handle the output graphics, the drawing on the screen. Um, the details between 8.5, the first version of the windowing system or graphics subsystem, and Rio's use of DevDraw are radically different, but the principle remains the same of managing multiplexing through managing conventional access to conventional names through the namespace. The main difference there is that it's done in such a way in the modern DevDraw to avoid having to put all the graphics output through the Windows subsystem. It's multiplexed at a different level, and the Windows manager really does just manage who has access to what, and what names each window accesses to get the graphics that it wants for that area.
So that's the windowing system.
Yeah, so the idea is there is that the Windows system is just a multiplexer of names.
Multiple names. Other innovations that this thing also brought about are UTF-8, right?
Yes, that was one of the earliest things. I think that was uh, slightly late 90s, wasn't it? And indeed Plan 9, which was just I think the earliest Plan 9 paper dates from 1987. So published announcement of it is a description of something from 1987. That was then revised considerably into the 1990s. I think the first time I saw a significant amount of information about it was at the London UK Unix user group meeting in 1990, and there were quite a few Plan 9 papers date from that that conference. I'm trying to remember. I can't remember whether ETF8 existed then. What was the date of that? Just Yeah, so that's 1992. So the version of Plan 9 that was being described at the conference was using some other scheme, some other Unicode scheme, I think, for handling of characters. One of the reasons they invented UTF-8 was to fix a lot of the problems with the proposed scheme, problems that came up when they were trying to implement Unicode for Plan 9, or make this sort of universal character set to replace ASCII and endless code pages and all sorts of other crud. One of the biggest things was that it wasn't compatible with ASCII in the sense that it wasn't compatible with ASCII, and ASCII wasn't a subset, and it wasn't file system safe because you couldn't look at a name. You might see slashes, but they weren't really slashes. You had to interpret characters up. Sorry, a byte encoding up to that to realize that no, it wasn't a slash. Really, it was some other thing. So it was hard to process. And broadly speaking, you might capture the real problem is it wasn't self-synchronizing. In other words, you couldn't seek into a stream of whatever the encoding was called and find the Unicode character. Um, you had to start at the beginning and then work through the various shifting and other encoding techniques that went along. So they devised UTF-8 notionally on a napkin at a local I think it was a sushi restaurant or something. Anyway, they came up with that fairly quickly and implemented it in Plan 9 to show that it actually worked. And so yeah, that was 1992 September. They invented it, and then hacked everything up in the Plan 9 of the time to provide one of the first implementations of it. I think it was the first.
And I mean, what that allows people to do is to still read all the ASCII encoding text that exists, while at the same time using Unicode characters as well.
Yeah, that's right. Well, I mean, a simple example, I mentioned the slash, and that's because if you did something like, the C library function structure or strchr to look inside a C string for a given character, you can do that with UTF-8 and it will work. If you look up structure path of slash, that will work. And I don't know about slash, but there are other characters that didn't work correctly in the original byte-oriented encoding of Unicode. So existing programs then at least don't do anything wrong. They might not know that they're dealing with Unicode characters encoded, but then again, I discovered when writing some of this stuff that a great many programs really don't care. They don't look in detail at it. You want to be able to get a path name, a URL, something from one end to the other. The things that look at it in the middle don't really care in detail what the individual characters are. They are interested sometimes in parsing it into a sequence of path names in a path for URL or file system traversal. And so it was it's just a big advantage to have that. Um, and also in Plan 9 to make it fundamental to the system. So there, there are libraries that will help you translate other code pages and other representations to and from UTF-8. But the system itself uses UTF-8 exclusively. Um, and so there's a host of things you don't have to worry about that, say, even recently, in the last couple of years, I've had to worry about when doing some Java programming.
Yeah.
Which character set are we doing now? It's I'm getting question marks turning up because somewhere
Right.
along the line it was going through 8859-1 still,
Right.
and you end up with this cascade of locales or hierarchy of locales, and you have to work out which one is active in a particular domain. And, yeah, all of that goes away or can go away, as Plan 9 is sort of suggested. And Go does it's in both Go and the Inferno language limbo that UTF-8 is sort of fundamental to both.
It seems like pieces of this got taken away, but what happened to the main distro of Plan 9? What did they decide to end up doing with it? Why
Well,
aren't we using
well,
it?
it's one of these things that first the original distribution was to universities, um, early 90, I think 92 maybe, 91, 92. Um, I was I was a sort of computer officer at the University of York at the time. Um, that it was released to universities, and I got an early copy and started doing stuff with it. And indeed, for a time, a bit later, I had it running on a collection of small x86 machines that we could use to populate student classrooms in the computer science department, not the universities at all, to provide the Plan 9 interface. But that sort of shows up the problems that you run into, which is that, well, there is this thing called APE, the ANSI POSIX environment, in Plan 9 to provide a portability environment. Um, but the programs that even at universities that people wanted to run and import once the network, once the internet had spread as it did in those years to nearly everywhere, and so people were beginning to distribute software that way, or even if it was still on, I don't know, tapes or floppies or something. It would be written to uh, either a particular Unix variant or to a POSIX uh, subset, and that means that you then have to take all these advantageous things in Plan 9 and ignore them in order to provide an emulator for POSIX to allow you to run the programs that you would run on any other system, taking advantage of nothing in Plan 9 when doing it. So the system isn't particularly helpful if you just want to keep everything the same. Uh, and so that's a practical reason why it didn't catch on. Is that and it's not just Plan 9. There are a number of experimental systems. I can remember attending a talk by, I think, Jonathan Shapiro about KeyCOS or some secure operating system. And he observed that you spend nearly all your time implementing the POSIX emulation layers on top of these things, rather than the stuff that the interesting new stuff that you wanted to do. So it's that practical thing, which is that there wasn't eventually there was an X11 implementation for Plan 9, but in order to get X11 compiled, you had to get GCC imported, and GCC is even then was a big piece of code. There wasn't too much support for C++. It was still using a version of CFront. And the only reason that was included with the Plan 9 distribution was to run one program, the PM text post processor by Kernighan. So it's, if you like, there's just this collection of practical problems. We applied it in various ways to do Plan 9 specific things, to take advantage of Plan 9 to build, if you like, an application architecture for a completely new thing. In other words, it wasn't going to be built using POSIX. It wasn't intended to run under POSIX. It was intended to run only in Plan 9. But that was probably fairly unusual over the years. So that eventually in 2004, I think, or maybe a bit earlier, Plan 9 was made open source, free software. And that meant that more people could get it instead of having to sign up as you did for the university distributions. But it was probably a bit, even that was probably a bit late by then. But that's just the way things happened.
So I guess in an effort to combat this, having to rewrite everything once again, the idea of Inferno comes up, right? Where you provide all those interfaces through a virtual machine. Is that a fair way to say it? This being the next thing that Bell
Well,
Labs worked on
the original,
for an operating system.
well, the original target, the hosted part was, yeah, several things. Yeah, the original impulse, as I understood it, at the time, was to provide an operating system for an AT&T set-top box. I think that was the original target. And that part of Group and Bell Labs had quite a bit of experience in doing operating systems of one sort or another over the years. And they felt that taking some of the ideas of Plan 9 and providing, and they also wanted the set-top box to be programmed in a reasonable way. So they adapted some things that had been experimented on in Plan 9 and earlier in terms of programming languages, and they produced the Limbo language for application programming under Inferno. So Inferno started off as being a system to run the with an initial target of a native port to a set-top box. The hosted part did, if it didn't exist immediately, it didn't take long to turn up. And that does have the effect of making a Plan 9's primitives, the names bit now, services as small trees of file-like things, namespaces that are computable, and a file service protocol to link them systems together, to provide to implement the services and also to link systems together. We're all taken into Inferno and used as, again, in the same way as Plan 9, as fundamental structuring schemes, mechanisms for the system. And it was a pretty short hop to go from converting the chunks of the plan. So the Inferno kernel was based on chunks of the then Plan 9 kernel. There was an experimental internal system called Brazil that was intended as a variant or successor or something to Plan 9. Out of that collection of older software, the Inferno kernel was made, and as part of that, there was realization that you can implement those little trees of things natively to control real devices, but you could just as well have them have the little trees run code that interacts with a different underlying operating system, a Mac, a Windows, a Linux, a Solaris. I mean, it's often easy to forget that even the different Unix systems of the time had portability barriers between them, hence the POSIX interest. And so it was, and if you look at the code of Inferno's implementation of the hosted part, which is called EMU, you can see that it uses chunks. It uses the same internal style and structure as a native device driver would use for a device driver, or it's just that it turns around and uses a Linux system call or a Unix system call or a Windows call to provide the same interface that you would see on Plan 9 or native Inferno. So it had the effect of exporting Plan 9's ideas into the wider network. And indeed, I still do that. I run hosted Inferno on some virtual servers running Linux. And I import network interfaces and other interfaces from those into Plan 9 or Inferno systems elsewhere using the 9P protocol. And the remote, so I can see the network interfaces on that virtual server under /net. I can make connections by following the conventional scheme of opening a file and writing a connection address into it and getting the connection and reading and writing it. And that actually has the effect of operating sockets on the remote virtual server. But the application isn't aware of that. It just uses the Plan 9 or Inferno mechanisms to access the services. And other services can be accessed the same way. It's less common, even though it's sometimes possible, to have the virtual servers access remote Inferno or Plan 9 services, but it can be done if it's not inside an EMU hosted environment. So the big thing about Inferno then is that you have these ideas of Plan 9, and it's normally the three things: either the resources as file trees, composable names or computable namespaces, and the file service protocol 9P to implement those things and also to provide distribution to and from remote sites. And those ideas are embodied inside the Inferno structure, but extended, because it operates in this kind of virtualized environment, to any system on which you care to put EMU. I mean, to do the EMU port. And over the years, there've been quite a few of those.
There's an Android one. I think it's a little out of date.
Yeah,
You can do it through the terminal as well, I believe.
Yeah, some of these would end up being experiments. The in a local, I've got a couple of devices that run other operating systems, and I've put EMU on them to be able to access those specialized things on those devices using Plan 9 or Inferno-like structures. The second thing, so there's that one level of providing Inferno providing Plan 9, carrying Plan 9 out into the wider network across a bigger range of targets, compared to Plan 9, which at the time was mainly restricted to native ports of one sort, one architecture or another, or having to run Plan 9 itself in a virtual machine, which is a reasonable thing to do. It's just it's perhaps heavier weight than some of the things you can do with Inferno. The second part was providing a programming language to do concurrent programming, first for the set-top box, and then for other potential Inferno targets. Hence the development of the Limbo language. For those who haven't seen it, very roughly, I just usually describe it as it has, broadly speaking, it has the syntax of C with bugs fixed. So, for example, in the equivalent to the switch statement, cases don't fall through, and the labeling is a bit cleaner. And it has a type system close, that's similar to that of, say, Pascal, but with the bugs fixed, so that there are variable length arrays as a matter of course, whereas in Pascal the size of an array is bound into permanently to the type. But the big addition in Limbo was the use of processes, concurrency through processes and channels. Uh, so there are channel values. A channel is a type, a channel of a chan of int, chan of chan of int, chan of chan of a structured type. And processes communicate only using communications on channels. As it comes, Inferno applications don't use mutexes, for example. It's very CSP-like, communicating sequential processes like HORS, uh, um, language invention or notation invention, and that's used for everything. Unlike the later Go, it doesn't have mutexes as a primitive type that are used as a matter of course. There is, I think, a Limbo module that does mutexes, but it does it using channels behind the scene, as its implementation. So the concurrent programming model it had is a strong and powerful one. It was originally interpreted, the Limbo language was compiled to interpreted code because a bit like, I suppose, the Python implementation is that some of the heavier duty computation required to carry out some of the functions was actually done by C, which is invoked through a foreign language interface between Limbo's abstract machine, DIS, and the underlying system. Underlying C libraries. So you can get the performance of C, but organize your application at a high level. So there were two graphics libraries. One was suitable for a set-top box, and the other was suitable for I think it was called Mux, and the other one was a variant of TK. A re-implementation of TK, simplified to use in many ways, and also using Limbo's channels to provide the event streams instead of having a big event loop. Say, there are reasons, those commercial reasons within the. One of the things that happens, Inferno was at some point intended to be a commercial offering, and so there was a business unit associated with the Inferno business unit, and its aim was to turn Inferno into a commercial platform for various networked environments. Inevitably, being a telephone company, one of them was an internet phone. Everyone was keen on internet phones with browser screens, but also a telephony thing attached. And then there were set-top boxes. There was a plan to have it used as the basis for a bit like X terminals, but higher level, more programmable, and similar things. But that a lot of these things came to nothing in the end. A fair amount of money was spent to do this and that, but there wasn't much adoption.
So those are the major innovations of the Inferno OS as it was, and where it was targeted for. How did you get involved with it, and what was your experience with it?
I heard about the system in '96, I think, and I happened to be not too far away, so I went to visit Bell Labs to see about this thing. So I'd been using Pan 9 type things in one or two commercial applications, not Plan 9 itself, but some ideas of how you build a distributed system or a concurrent system. And this sounded pretty interesting, so I managed to go to see it. The first problem was that at the time, a source code license was millions of dollars, which seems weird now, but it's because it was whatever Sun was charging for Java at the time. and both systems were closed source. Inferno was closed source. Uh, well, yeah, that was more than I had. Even so, in '97 we formed a company to. That was the first Vita Nova to do something with these technologies. The aim of doing that. One of the breaks was that the business unit wanted a demonstration. We separately, as part of another company, we'd done an internet game, sorry, a networked game playing, real-time game playing system, and which eventually turned into BT Wireplay. Then they got bought out by someone else. And the Inferno business unit were looking for some sort of interesting demo to have at Comdex in '97. And so we agreed, one of the more senior sales guys came up, we agreed to do a networked Doom game for them. And I did, the first problem was that, well, we can't give you the source to this or that. Well, it has to run native on a PC as a multiplexer, or it's just a silly demonstration. It's a pointless demonstration. So one way we did get the source code to do. I did a native port. There wasn't a native port in the business unit at the time to a running one to a PC. There was in the research group, but there wasn't in the business unit for complicated reasons. So I did a port of that to a machine, a little server, and that became the multiplexer using 9p. At the time, it was called Sticks, and it was slightly different, but we'll just use 9p forever from now on. And so we did. So and there were DOS machines running Doom, but they communicated with the multiplexing server for control things. They imported a 9p service or export and use that to access things, services on the Inferno box, which was running on a native PC, and that worked really well at Comdex. Then it went a bit quiet, but backing up a long way, when I was working with Plan 9 at the university, I did a port of Plan 9 to the PowerPC. Well, sorry, the Power Architecture, which then became the PowerPC. And I did some more work on PowerPC stuff, do little boards and so on. After Comdex, things went quiet, but then they had a problem, which is that they needed a port to a PowerPC and an Inferno port to PowerPC, and they didn't have anything. But I had done a port to a native port of Plan 9 to a PowerPC, including the compiler suite, so they got me. We reached an agreement with them that the Vita Nova would do this port, and I flew over and back and forth. Flew over to find out about this stuff, and then came back to York and did the work, and then shipped it across the Atlantic. And someone in the business unit tested it on the set-top box that was the target. I think I got one of the set-top boxes shipped to me at some point. So it's really because I had this, I'd done this Plan 9 PowerPC port earlier that led to us eventually getting a sort of technical services contract with the business unit to do Inferno-like stuff. So to do work on help them with the Inferno development and including commercial targets for ports and so on. And that continued with adding more people along the way as the amount of work grew. There was a Minitel emulator that we did, and which is I left it in the distribution because it's an interesting example of the use of concurrent processes and channels and so on to put an application together. until about 1999, and at some point in 1999, the Lucent decided it didn't want to have a business unit doing Inferno, and it was going to be spun out as a sort of an external startup-ish kind of thing. Um, and yeah, through a lot of steps and missteps, we ended up acquiring it from Lucent, um, and and then we set about doing things with it. One of the first things we did was to create a programmer's manual for Inferno that was similar to the and other documentation, other documents that was similar to the the famous manual pages for Unix and manual pages for Plan 9. So we provided detailed documentation for each module in the system for the things that correspond to system calls. And Richie had some initial uh, um, 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 collection of manual pages that had been abandoned, so by the business unit when they switched to FrameMaker or something. So he sent those across, which provided an initial set. It wasn't very big. And then we went through and documented everything in the system and checked that and produced the first programmer's manual for it. Commercially, the aim was to provide a system of, provide the system under, it wasn't free software, it wasn't open source exactly. You got the source in exchange for a subscription, and the cost wasn't millions anymore. It was maybe, I don't know, depending on your category, I can't remember now. I think it might have been as low as a few hundred, 300, and as high as many thousand if you were some sort of organization. Um, and we got some interest there, but it wasn't really it was complicated because at some point, Plan 9 itself was released as open source. I can't remember whether it was 2000 or maybe. And so that sort of collided with it, and then we had to make a decision at some point about whether we open up Inferno itself as free software in some way, which eventually we did. But it meant that you didn't get any income from the basic system. Instead, one mistake we made originally was to prepare and sell the system without having a particular application as part of that. It was done for a reason, which is that we didn't think that the approach of picking an application area worked well for the business unit, and we didn't want to make the same sort of mistake. Later, we did an application area, which was the Inferno grid, a computational grid that built a computational grid out of whatever computers you happen to have lying around your system, whether running Macs or Windows or Linux systems or servers or laptops or desktops, and turn that into a big computing system to run through a kind of big batch job. And that was used by a reasonable number of people, including a drugs discovery company in Oxford used it for quite a while. It was some. There are a few. What was the? Sorry, I can't remember the name of some other systems that also built computational grids out of odds and ends workstations. But there were a few. But we used Inferno to make the control interface, the graphics interface for it, completely portable, and also to allow it to run on a variety of systems. The server could run on a Linux system or whatever else you had that was suitable. And it was put together as the system scheduler, the distributed scheduler was clients access that by inputting a namespace from the server that allowed them to submit and or to fetch jobs, work to do, depending on the characteristics, to submit to submit control requests for the admin user interface, and to submit results when they had them. And all those things were done using 9p and little namespaces to control the scheduling and to provide the work. It was really clean, and it was put together. So one of the things about providing services as file-like things is that for initial development, you can actually just make them real files. So you can write the user interface against some files that you stick in a directory that have the right stuff in them, and see that you have processed that stuff correctly. Similarly, the scheduling element can have a collection of files that have the right contents in it to represent jobs, the control requests that have come in, and check that the scheduler behaves correctly using those. And the client can be tested. The client that's taking the work can be tested in a similar sort of way, and then you can put them all together. So you can get some parallelism in development, and that's indeed what we did. Is that one person did the scheduler and one person did the user interface, and all we had to do initially was to define namespaces for each one of those functions and get them to program to that. This was globally agreed that these were the namespaces, and then people just implemented using the namespaces as the sort of specifications of what they had to do. And that worked quite well. And we then migrated into doing the AMD64 port of the Plan 9C compiler suite for use on an AMD64 that was part of some supercomputer project, I think, originally. And but that then turned and that became useful much later when the initial Go compiler was being produced for the AMD64. And also the PowerPC reappeared because we had this idea of running Plan 9 as the operating system. It's a distributed system. We had the idea of running Plan 9 as the operating system of a Blue Gene, several models of a Blue Gene supercomputer, and that went on for a few years. And we built we built new network interfaces, software interfaces to the networks. At the time, the Linux one was done by emulating, making these weird networks look like Ethernets, whereas we made the weird networks look like what they were, and addressed as what they were, and used Plan 9's general connection service and other facilities to make that work. And then it all stopped. But I went on to do some other contracting, and people continue to work on Plan 9, but the original group had left Bell Labs for Google a long time before, and somewhere along the way there was this because you mentioned Ninefront earlier. There was an alternative working group, implementation group. Another group of people got together who sort of liked Plan 9, but they felt a bit excluded by whatever it was we were doing in the sort of official release. Some of that was the result of some perception of some of the Ninefront stuff being a bit politically difficult. But that's all gone. And actually for years now, a good few years, there's been a lot of really interesting work being done in Ninefront. And the people involved are, there's a group that they have hackathons periodically. They sort of care about things, and they care about the quality of things, and they care about the novelty of the system. They care about the Plan 9's own compiler suite being maintained. And really a lot of the action sort of turned up in the Nine Front area. Um, and they have done some quite interesting things. The And alongside all that, I suppose since 2009, there's been the whole Go business. It took me it wasn't until quite late that I sort of got interested in Go and not complaining about it all the time. But it has taken the processes and channels model, not just from Limbo, but from the thing that Limbo got it from, and so on. And the big difference between it and say Inferno and Limbo is that Limbo has with Inferno this operating system layer, and I think it's quite a powerful. I think it's still quite a powerful construction. I think it's useful to have that. It simplifies things. Go, in many ways, is very conventional. It just has it has a very useful and a standard library, but it uses libraries, a collection of libraries and library interfaces to do things that in Inferno would be done by having a namespace for it, say. And so there are actually a lot of interfaces inside Go, and it makes it good for people writing conventional servers and doing conventional things, but you don't get that structural simplifying that you do, or that structural effect that I mentioned at the beginning about Unix and being in a world of its own. Is that the Go environment is just the same as Java, except that it might be implemented differently or better or whatever, but it's still a programming language with a big runtime system and libraries, rather than having this operating system layer to allow you to run the same thing everywhere.
I do have one more question for you, and that is, what about this stuff still keeps you interested? Why do you still work with it? Why do you still like it? I feel like a lot of the stuff has evolved. It seems like other operating systems have taken the bones or bits and pieces of stuff.
Every time I look at some of the things that other things do, I get frustrated because it's just so much easier than Plan 9 in it, and it's simpler. Yeah, to be blunt, the control groups and parallel system call universes and capabilities that aren't really capabilities; they're just sort of flags. There's some interesting things you could do with proper capabilities, but that's not them. And well, even things like in Plan 9, the way you get a new network stack independent of the other ones is you use a different instance of the service that provides the network stack, or say the TCP/IP stack. And you just put it somewhere else in the namespace if you want to see them both at the same time. The thing you have to do in Linux and other systems is a lot more than that, put it that way. And you have all these jail things, and even those are pretty old, some of them. So I just don't find that there's the same. Yeah, a lot of these things don't make things any easier. They're just more complicated. And I prefer things that somehow make your life your work easier, quicker to do. And so I do look for opportunities to apply at least the ideas in other application structure.
Is there anything that you'd like to promote with regards to Plan 9 or Vita Nuova or anything like that?
Well, Vita Nova is sort of in mothballs. At the it's a fiddly business to for various reasons to do with shareholder structures and other things. It's fiddly business to shut it down, but it hasn't been doing anything for a good long while. So I work as a contractor for the most part. So I don't. I would. I would say, well, you could try having, just having a bit of a play with Inferno. But as you probably know, and it's come up just recently on the Inferno list, gradually systems have stopped being able to run 32-bit code, and Inferno, in its original core, was a 32-bit system, and there was never any big need to move to 64 bits until systems stopped running 32-bit code. Latterly, just in the last 5 or 6 years, I suppose, various people have made attempts to do 64-bit versions, and one of those will become official. But until it is, it's a bit frustrating for people. I'd say, go and try it, and they go, I can't get this thing to work on my machine. So but I think it's worthwhile having a look at. I would certainly suggest that people should go off and have a read of the papers and the Plan 9 papers and Inferno ones to just to get some ideas going. Even if you're not actually going to be programming it, and see how it's used. There's I think there's one where I brought together as many examples of the use of namespaces. The ubiquitous file server in Plan 9, I think, might be the title. I mean, obviously the original papers by the original designers are critical to read first to get some idea of the ideas behind it and the impulse behind it. I mean, a lot of the original, I think most of the original developers aren't using the system. They sometimes use the tools, but they don't have access to, or don't make use of the namespace notions, or the even to some extent the file server stuff. So I suppose the best thing to promote is to have a look at the papers to have a look at the ideas. They're the things you don't want to be lost forever, and maybe people can think of ways of applying them as they're doing other stuff.
Well, Charles Forsyth, thank you very much for speaking with me. Thank you.
Okay.
As always, you can email the podcast at don@livinginthefuture.rocks. Thanks for listening.